So, as I said before, we are going to study about the half adder using nand gates, full adder, and the full adder using the nand gates. So, first thing is the half adder. In Viva, there will be many questions asked about the half adder. They may ask you to design the half adder using XOR and AND gates. That's the basic question. And they may ask you to design using the NAND gates just to draw the circuits. And maybe ask what are the inputs, what are the outputs, how the output differ from half subtractor, like that. So we first study about the half adder. First we design half adder using the XOR and AND gates. The XOR and AND gates. How can we construct a half adder using XOR and AND gates? It's quite simple. So you have to you just need to study what are the outputs. So from that you can easily create the implementation of the circuits. Okay, by practicing this you can when it comes to complex circuits, from just the result from K-map you can easily construct higher level of circuit. You don't need to by heart the diagram or anything. From just the these equations you can construct the circuit. So first here for the half adder we have studied the sum and the carry. The sum equation for the half adder is A XOR B. Okay, and the carry of the half adder is nothing but AB. What is A XOR B? XOR B is nothing but AB plus A complement B plus A B complement. Okay, how you get this? These are inferenced from, the answer is got from, is a result from the K-map. Okay, let's see how we draw the K-map. How first we need to make the truth table. From that we will make the K-map. From the K-map we get the answer for the sum and carry. While after we get the answer for sum and carry, we will design the half adder. Okay, so let's create the truth table for the half adder. Truth table. Okay, we needed two inputs. Okay, from this we got one source of information that half adder have 2 bit of input, while full adder have a 3 bit of input. Okay, so half adder have 2 bit of input A, B, and we will have a sum. Okay, the sum of A and B, and there comes a carry which we will denote as C. So as it is a 2 bit, there are only 4 combinations: 0 0, 0 1, 1 0, and 1 1. So what is this sum of A plus B? Means 0 plus 0 is 0, and the carry is also 0. For the sum of A plus B of 0 and 1, the sum will be 0 plus 1 1, and the carry is 0, right? For the 1 0, the sum is 1 and the carry is 0, right? There is no carry. For 1 plus 1, how is 1 plus 1 in binary added? 1 plus 1, sum will be 0 and the carry 1 come out here. Okay, that is a carry. That's the carry. Okay, this 1 0 means 2. Okay, 1 plus 1, here sum is 0 while a carry is 1. Okay, as simple as that. Now we can construct the K-map from the truth table. As it is a 2 input and 2 output, is a 2 by 2 K-map. A and B. First we look for the sum and then later we look for the carry. Here comes the carry, the A, B, and this is the carry. 0 0, 0 1. This is 0 and 1 only. This is 0 and 1 only. Here also 0 and 1 only 2 bit, right? 0 1 0 1. Look for the sum. When will be the sum coming 1 here? In this case, the sum is high. High means 1. What are those cases? When AB becomes 0 1 and when AB become 1 0. Now mark these in the K map. 0 1 and 1 0. Okay. So as these are diagonally, we cannot combine them. Okay. So what is our output? Is 1 0, which means A B complement plus this A equal is A 0 and B is 1, which means A is 0 means A complement and B is 1, which means AB. What is this? This is nothing but A XOR B. You have to know the what is the input of A XOR B. This is nothing but A XOR B. And what's the carry? Look at the carry. Carry is high when A and B is 1 1. Look at 1 and 1. This case only. That is nothing but carry is equal to 1 A B A B. So we get sum as A XOR B and carry as A B. Now let's implement the implementation. I mean the design. How we implement? Have a look. So the sum is A XOR B. So we need two inputs A and B, and the sum is A XOR B. This is A XOR B, and we need the carry AB. So let's take from A and B, right? Yeah. This is the carry. This is nothing but AB. That's it. That's how we construct the nothing but the half adder using the XOR gate and AND gates. And there is another question. We have to construct this by using XOR and the NAND gates. How we construct this using XOR and AND gates? Let's have a look. It's very easy, absolutely easy. You need to convert the AND. How is AND in NAND? How we convert AND to NAND? It's very easy. First we have to put a NAND, then it becomes AB whole complement, AB complement. Then use another NAND, then it will become AB. Simple. Okay. Then you have to do this thing from AND to NAND. Okay, AND gate using NAND gates. Okay, as it is simple. So you just replace the AND with these two NANDs. You get XOR using, half adder using XOR and NAND gates. So we constructed the XOR gates using the AND gate and using the NAND gates. And this is how this is constructed. Now let's move to the full adder. So now let's move to the next one, which means the half adder using NAND gates only. We completed the half adder here. We have where to do the half adder. Oh, you guys not seeing that? Okay. Half adder using NAND gates. How can we convert the previous half adder using NAND gate? Now let me take the one. So how you can convert the half adder using the NAND gates? So this is a half adder that we made before constructed using the XOR and AND gates. Now we will construct it using the NAND gates only. Okay. So first we have an XOR gate, right? We had an XOR gate here. Then we connected using an AND gate. In the previous video, I teach you how to draw an XOR gate using NAND gates only. Okay. Now let's first implement that. How to draw the XOR gate using NAND gates. There are two inputs, A and B. Okay. Now let's construct the XOR gates using the NAND gates. I'm sorry. Okay, yeah. This. Okay. We construct the XOR gate using NAND gates. Connect this to here, this to here. My drawing maybe is quite not much good, I'm sorry for that. And connect AB here, then this as its input, this will be the sum, and here one more thing, take this and connect like this, so we get the sum part. Now we have to do this is A XOR B. Now we have to do the what, the carry part. From where we have to connect the carry part. This you have to use some trick for easy memorization. Use for the half adder using NAND and half subtractor using NAND, which can also be applied for half and full adders also. Now let's see how can we do that. For carry we need what? Nothing but AB, right? From here we get AB whole complement. Okay, from this AB whole complement we need to convert to AB. So it's simple. You have to take this, or just take from here or here, anything. So I am taking from here. It's the same, right? AB whole complement, AB whole complement. Or you can take from here. Okay, take from here and come to using another NAND which convert it to AB whole complement, another complement which is nothing but AB, which is our carry. Simple as that. So we constructed half adder using AND gates only. Now let's move to now let's move to half subtractor. Okay, half subtractor. So as we study in the half adder, there comes sum and carry. Here comes the difference and borrow. Okay, here comes the difference and borrow. After we study the half adder, means normal half adder and half adder using NAND gates, we will move to full subtractor and full adder. Okay, I think that's more convenient. So let's study the half adder. Half subtractor. We already studied the half adder. In half subtractor, first we will study about the using XOR and the NOT gate only. NOT gates, which means this is a normal XOR gate, which means a normal half subtractor. Now, as I said before, construct the truth table: A, B, difference, and borrow. So the inputs are 2, which means 0 0 0 1 1 0 1 1. Symbol 0 minus 0. What is the difference? Difference is 0. What is the borrow? Borrow is 1. Why? No, borrow is 0. I'm sorry. So 0 minus 0, difference 0, borrow is 0. 0 minus 1. What thing will come here? As you know, is 1 0 minus 1. Just construct this question. For 0 minus we cannot do that. So we cut the 0 and make it as what? 1 0. 1 0 is what? In binary it is 2. So 2 minus 1, the difference is 1. So here the difference comes 1. And the borrow, what is the borrow we take from here? It is a 1, right? So the borrow is 1. 1 minus 0, difference is 1. There is no borrow is taking, so 0. 1 minus 1, the difference is 0. And the borrow also is 0. Now construct the K-map. A, B. K-map for the what? For borrow, for difference first. Then we can connect the K-map for, construct the K-map for the borrow. For the difference, the 1 comes in this and this part only, which means 0 1 and 1 0. 0 1 0 1. 0 1 and 1 0, this and this. Here the difference is a b complement plus a complement b, which is the same as before, which means ax or b, right? For here, there's only one part, which means 0 1 0 1 0 0 1, this only. Okay, which means the borrow is a complement b. Simple. Now you can take a, I must say, pause the video and construct the half adder by your own. After that, come back to the video. Okay, now let's construct using these equations we gained from the K-map. So the difference is ax or b, and the borrow is nothing but a complement b. How we get the difference? We get the difference ax or b. We need to use an XOR gate, same as for before the half adder. We get the difference. And a complement b. For that, for a complement, we need to use a NOT gate for the complement of a. Now the a becomes a complement, and we take the b from here and we multiply using the NAND gates, and we get a complement b. Simple. This is how we I guess you guys can see this. This is how we construct the half adder using XOR and NOT gate. Now, as a final step, we have to construct this using the NAND gates only. So let's construct this using the NAND gates. I think this space is enough for constructing using the NAND gates only. So as I said before, convert XOR gates into NAND gates. I explained this in the part 1 video. So convert the XOR into NAND gates. This one here, one down, one here, and there will be a connection like this, and A, B, and from AB to here, and from both sides to here. Simple. Okay, then we have A, B, and here is nothing but the difference come. Okay, from here we need a complement b. How we take a complement b? From this, from the output we get here as ab whole complement, right? From that ab whole complement, there is a b coming through this, right? Which means it comes as b ab whole complement, and we know by using De Morgan's theorem we can get this as, by using De Morgan's theorem, let's solve this equation, which means b complement plus a complement b complement whole complement. How this was, which means b complement plus this a complement a plus a plus b and b complement, or b 1 0 is what, 0, right? Which means ab whole complement. So we get the outflow. So from here we get what, a b complement. But what we need actually a complement b. For that we use a NAND gate, which means the negation of this we get as a complement b. Simple as that. Okay guys, so we're done with the half adders. Now next we will move to the full adders.